So it's 9 a.m. sharp in UK time. We are moving to the third speaker of this session. Dr. Shahrooz Janbaz is an assistant professor at Malik Ashtar University in Iran. I know him from 2015. Before starting my PhD, I was looking for applications of algebraic geometry, and one of the keywords that popped up was coding theory. And through one of my classmates, I was informed about Dr. Shahrooz Janbaz's class on algebraic coding theory, and I went one day sitting in his class, and it was a very nice lecture. So I know him from that time, but now we are lucky to get a new talk from him. Dr. Janbaz, please go ahead.
Hello, everyone. Thank you very much that you invite me to this talk. As Amir Hussein said, I'm working on recently I'm working on quantum theory and its application. My talk is about coding theory from brain to quantum. We have many phenomena in the nature, but the fundamental of many of these phases is unique. I want to begin with two different kinds of problems, and we will see that these different kind of phenomena has the same roots, which is coding theory. In one side, we have Mariner 5, which is used for photographing the deep space, and in the left, you can see the hats with many colors. So what is the relation? What is the relation between hats, colorful hats, and Mariner 5? Actually, Mariner 4 and 5 in 1965 up to 69 took the first photographs of another planet, 22 photos. And each photo was divided into 200 multiplied 200 elementary pixels, and each pixel was assigned 6 bits representing 2 to 6 or 64 levels of brightness. And for this work, engineers used Hadamard code. And what is code? I will explain about it. And the transmission rate, which helped you to see good picture, was 8.3 bits per second. But in 1970 up to 72, Mariner 6 to 8 took such photographs that each picture was broken into 700 multiplied 832 pixels, and the engineer used Riedmuller code with parameter 32, 64, and 16, and the transmission rate was 16,200 bits per second, and the photographs, the quality of the pictures goes much better because of the new code. And so we can ask, what is code that is used for these missions? Another phase of our view is about game theory. We have a famous problem in game theory, which we say hat guessing games. We have a team of n players enters a room, and each receiving a hat of a random color from among available colors with equal probability, and we have a lot of colors with one. We have a lot of hats with one color. Each player can see the color of the other player's hats, but cannot see the color of his own hat. And players must guess the color of their hat or not comment until they can pass their guess. If a player guesses incorrectly or all players do not vote, the team loses. Players can determine a specific strategy before the game starts and share it with each other, but they have no communication with each other inside the room. So it's a kind of silent game. with predefined strategy, and it's a cooperative game. All players must cooperate to win the game. And it's a famous game. New York Times has a nice paper with name "Why Mathematicians Now Care About Their Hat Color." So we have a game, and we have to solve it, or we have to find a strategy that guarantees highest probability of victory of the team. We say in game theory that it is a winning strategy. Let me see a simple case when we have two people and three colors for hat, and we see three strategy here. Method one, random selection strategy. Each player randomly select the color of his hat and say it. We can see the gain of this strategy is just 26%. A very difficult question is, do we have a better strategy for this game? And method two is another strategy, a player's guessing strategy. In this strategy, all players except one pass their guesses, and one player guess their hat color, his hat color. And with this strategy, the gain of this strategy is 50%, and we can see that we can do better than the previous strategy. But the very trickiest, we have a very tricky strategy. We say repetition code strategy. It is a little tricky, and we wrote a paper by my student about it. You can gain with this strategy 75% chance to win. And what is repetition code, or what is code? Again, we use a terminology with name coding. So we want to know what is coding, which is used in Mariner, which is used in game theory, and we will see that it will be used in many other direction sites. Actually, coding theory has many branches, but line coding, compression, but I want to talk about error correction code, or error correcting code, which is one of the most interesting and applied part of mathematics and informatics. Actually, all communications, which is digital, if you use fax, internet, or satellite, mobile, cell phone, any devices, you're required to use error correcting for best communication. The conceptual framework of the coding theory is this. You can see in this picture. You want to send a message, or you have a message source, and you have a message W. You have to encode it because you want to send it through the channel, and channel has some fundamental and nature property. We say it is noise, and noise destroys the message. So we encode the message, and we make CW and send CW into channel. Noise will destroy some bits of the channel, the message. So we have to, after we receive the message, we have to decode it, and we make the message W, and user use the message. For example, if we want to send yes or no in the channel, and we use just one bit, 1 for no and 0 for yes, and we send it to channel, and noise destroys 1. I mean, convert 1 to 0. When you receive 0, you think the sender sent yes, but the sender sent no. We use redundancy or encoding. It is a repetition code. We send 5 0 for yes, and 5 1 for no. If noises destroy 2 bits, bit 2 and bit 5, you can see that we receive 01001. In the decoding process, we count the number 0 and the number 1. We have 2 1 and 3 zeros. So it is much similar to string 0, and we decode this received word to the all 0 bits, and we see that we can read yes. So we corrected 2 errors in the channel. It's a majority decoding. It's the framework of coding. I will explain very fast and simple with the code, and I will show that the many applications of coding. A code C over an alphabet sigma is a subset of sigma star. It means you make all strings with all lengths by alphabet in sigma, and you choose a subset, and it is a code. A binary code is a code over the alphabet 0 and 1. For example, C1 is a code with length 2. You have 2 bits and 4 code words. Or C3 is a code on alphabet 0 and 1, and you have its length is 5, and you have 4 code words. With notation, NMD code C is a code, and we say N is the length of the code word, M is the number of code words, and D is the minimum distance of the code, which is the computation of the minimum distances is very hard in general. You can see we have to compare all code words and find the differences between 2 code words. In this case, you can see the differences between 2 code words is 3 position. So the distance between 2 code words is 3. The minimum of all the numbers are minimum distance, For example, this code is 241 code. The minimum distance is 1 because the distance between this word and this word is 1, and it is the minimum distance between all 2 code words. And C3 is 543 code. Our goal is to make an NMD code with a small n and large M and D, which is very difficult in general to you make good code, and there are many open problems in coding theory. The coding theory developed by the famous mathematician Claude Shannon in the Bell Company in the paper A Mathematical Theory of Communication, which is a very interesting paper, and there are many deep relations between this paper and statistical physics. I will explain if we have time. I want to show the many phases or applications of the coding theory. First one, our brain. Our brain is developed in such a way that corrects many noises. Imagine you are trying to read a sign in heavy fog. Your eyes barely pick up fragments, but your brain fills in the gaps. It's a kind of error correction in action, actually image correction, or image coding and encoding, or stream encoding and coding. Our brain are constantly interpreting incomplete or corrected signals. They guess, feel, and correct automatically. Cognitive scientists believe that neurons encode information redundantly to handle biological noise with chemical signals or firing rates or many other parameters, electromagnetic field, and many other parameters. So brain is a decoding machine, and it's evolved over millions of years for best decoding when we see many pictures. In biology, coding theory has many applications. Actually, DNA uses quaternary alphabet, ACGT. When cells copy DNA, they sometimes make mistakes. But evolution has built repair mechanisms, redundancies, and error correction for building best DNA string. So researchers in biology uses coding theory to understand how genetic mutation affects organisms. Improve gene editing techniques like CRISPR even store the data in synthetic DNA, which is very interesting field, DNA computing. And in DNA computing, you need a lot of error correcting for correcting the data on the alphabet ACGTP. So quantum noise isn't just a nuisance, it's a law of physics. And for example, in quantum theory, you can't copy a qubit. You must destroy a qubit and for copy it, and it's very different in than classical bits. So what do we do for what we have to do for doing the quantum computer best possible answers or do the best works? We have a quantum error correction. In quantum error correction, you must correct the errors which lives in the world of quantum. For example, phase error. For example, and you don't copy the qubit. So it's very tricky and difficult. Actually, scientists developed some techniques in coding theory, and we know quantum coding theory, for example, shortcode, and it's the shortcode, one logical qubit will go into 9 physical qubits. What is logical qubit and what is physical qubit is difficult to explain, but if we don't use quantum error correction, we don't have quantum computer. Quantum error correction design stable quantum memories and stable quantum circuits and scalable quantum computers. What's the next? What's the other applications of coding theory? Neural coding meets AI. Okay, building brain-smart system that learns how to correct themselves. In this field, you can use coding theory and merge quantum and AI for automation of correction. Quantum communication. We have QKD, quantum key distribution, or quantum internet, which needs quantum coding for correct noise in the quantum world. Bioinformatics and synthetic biology were designed artificial life forms with coded genomes. If one bit in the genomes change, the creature must will different many with other creature. So coding theory is not just about fixing errors, it's about understanding the structure of information itself. Actually, in the recent research with name constructor theory, the researcher wants to show the universe is an informational media and uses information for evolution. So the universe is a giant quantum computer. In constructor theory, we want to find the meaning of information. And in this field, coding theory and redundancy for correcting the errors in the media has a very important role. So I hope you enjoy coding theory and use many softwares and many other applications to test coding theory and use it. Also, if Amir Hossein likes, I have an open problem for undergraduate students with $20 prize, and I can send it, and the students can work on it, and if one of them solve it, will win the prize. Okay, that's my talk. I hope you enjoy it. If there's question, I am here.
Thanks, Dr. Janbaz. It was very inspiring talk. I liked it a lot. And sure, if you want to send it the problem, we put it on the website, and we put your email for sending the answers to you for the prize.
Okay.
If anyone has a question, can raise their hand. And Said Qurbani?
I really enjoyed your talks, and I was wondering, and I have a question. Do you think ideas from how the brain deals with noise could actually help in building better quantum error codings?
It's a very nice question. Actually, in coding, in quantum computing, you have a special noise, which is depend to the fundamental laws of physics. If we have common phenomena in the quantum laws and in brain mechanism, yes, we can. But in general, I didn't see any paper about idea about quantum theory, quantum coding, and the field of brain error correction.
Thank you so much.
One question I will ask myself. So near to the end of your presentation, you said try some software for testing coding. Do you have any suggestion for this software? Maybe naming one or two?
Yes, a very interesting and powerful software is Magma. Magma algebra system. Also, Sage is open source software, and a student can use it. But Magma is very powerful, but it's under license of Sydney University.
The previous speaker was also advertising Sage Master. It's interesting that people in different areas are using same software. That's interesting. Any other question from the audience? Peso, do you have a question? Oh, Jonah.
Yeah, thank you for a very interesting talk. Just wanted to ask, since quantum bits lose, I think from my understanding, they lose their states very fast. So we can't create copies of things as we have to destroy them, if from what I understand. Then how do we build maybe programs like artificial intelligence that has to remember record of things? Like, will artificial intelligence applications work on quantum computing, and how would that work?
If I understand true, you asked two questions. One is about the non-canonic theorem in quantum mechanics. In quantum mechanics, we have a theorem that we prove it, and it not depends to the devices or the speed of the copying. It's a non-canonic theorem. In non-canonic theorem, you can't copy any state of quantum, any quantum state, unless you destroy the state. With any technology, we can't copy the state of quantum states. But there are many strong relation between AI and quantum. We have a terminology says quantum AI, quantum machine learning, or quantum AI. And there are many benefits between them. Yesterday, I studied a paper which compared AI strangeness and quantum strangeness, and how we can combine these two different fields. If I understood your question, if not, please explain again. I answered.
Yeah, you answered most of it. Was just wondering how does training of AI model works in quantum computing, like just a brief idea on how that would work?
It is very tricky way. It's depend on your algorithms, but typically we use entanglements of node in CNN, convolutional neural network. The nodes are entangled, and when you transfer any weight on the edge of between the nodes, all nodes can affect by the weight of any other nodes by entanglement, and the nodes are in the superposition states, so can by intelligent measuring they can collapse in many different cases other than classic real. So it is very difficult because there are many books I can introduce you to which talks about quantum machine learning and quantum AI. But briefly, the idea was it's explained to you.
Yeah, thank you very much. Thank you, and also thank you for your amazing talk.
Okay, you're welcome.
Any other questions from the audience? So yes, maybe I will ask Dr. Janbaz to send the name of the books, and then I will share it with everyone later.
Okay.
Okay, if that's all the questions, then let's thank Dr. Janbaz with the clapping react.
Thank you very much.